Okay, so I have an integral for you guys, and the integral is deceptively simple. So you guys would think, or to the uninitiated in integral calculus, or who, if you guys have just reached U substitution, haven't gotten to trig sub yet, or alg sub, you guys would think that this would be simple. It would be a simple substitution, and you guys would think that it would just be straightforward from there. But it's not like that. So the integral is the integral of the square root of 1 minus x squared dx. And again, it looks deceptively simple to the uninitiated because it's just something, it's a function under a square root. I could probably just substitute that with u and then take the du, and then maybe stuff will cancel out and stuff would get simpler. But in fact, that's not what happens. In fact, we get a much more complicated integral. So, what I actually want to do is teach you guys about trigonometric substitution. So trigonometric substitution is another variation, you could say, of algebraic substitution. It's a special case of algebraic substitution wherein we substitute our x variable with a trigonometric function like sine, cosine, tangent. Those are the three main functions that you substitute things with in order to simplify the integral into a simple trigonometric integral, which we can evaluate and then we can return it back to our original variables. So for this kind of substitution, so in general, if you have a function or if you have something that looks like an a squared minus an x squared under another function, so I would have an f of a squared minus x squared. For example, f is simply x negative uh, to negative 1. So that would be 1 over a squared minus x squared. So you would use the substitution. So I would say, or this would imply, the substitution would be x. So I'm going to pick x is equal to a sine theta, or any variable. I'll use mu to denote that it's any integration variable. Now, if my function is of the form, or if the integral is of the form wherein I have this term, so this time would be a squared plus x squared, or x squared plus a squared, my substitution would then be x is equal to a tangent mu, or tangent theta. Now, if it's f of, it would look something like uh, x squared minus a squared, then it's different now. I would be using x is equal to a secant mu. So usually this form would be something wherein I would have something like x f of x squared minus a squared. And that's obvious from the fact that the integral of dx over x square root of x squared minus a squared is equal to 1 over, no, the secant. So it's partly because of that would be equal to the arc secant. So 1 over a arc secant of x over a plus c. Okay, so it was partly the motivation for this definition, the third definition here. So, of course, since I have a 1 minus x squared, I'm going to pick the first form. So I'm going to pick x is equal to, my a would be then 1 over here, because the square root of 1 squared would just be 1. So that would just be sine mu. So now, to substitute, I have to find my dx, which is cosine mu, d mu. Okay, and so you'll notice that when I take the square root of 1 minus x squared, that will be the square root of 1 minus sine squared of mu, or sine mu squared, or sine squared of mu. Yeah. So the square root of 1 minus x squared will be equal to the square root of 1 minus sine squared mu. And notice that, I want you guys to notice that This over here is an identity. In fact, you guys recall from your algebra that, or trigonometry, that sine squared of theta plus cosine squared of theta, or the reverse, cosine squared theta plus sine squared theta, is equal to 1. So this means that I would be transposing the sine to the other side, and I would be leaving a cosine on the left side and a 1 minus sine squared on the other side. So this is simply equal to the square root of the cosine squared of mu. And the squares will cancel out. The square and the square root will cancel out, leaving me with a cosine mu. And that's neat, because that's what we have left instead of the square root of 1 minus x squared. So cosine mu is arguably simpler. And my dx would be simply cosine mu d mu. And so this would become integral of cosine squared of mu d mu. And you guys can use a double angle identity from this one. So recall from the identity that cosine squared mu is equal to 1/2 times 1 plus cosine 2 mu, or 2 theta. So I can replace that in my integral. So it's 1/2 times 1 plus cosine 2 mu d mu. So I can bring the 1/2 to the front, and I can split the integral. This plus 1/2 integral of cosine 2 mu d mu. And this is where I can use a simple use substitution, wherein I'll just put a 1/2 at the front, and then I can directly integrate this into a sine. So this gives me 1/2 mu plus, so I would be leaving a 1/2 at the front, so that would be multiplying with the 1/2 already at the front, leaving me with a 1/4. And this is a sine 2 mu, because the integral of cosine is simply sine, and that's a plus c. Okay, so now that we've evaluated our integral, we've gotten rid of the integral sign, we want to put this back into the x world. So to put this back into the x world, we go back to our identity over here. So mu, to find mu, because we have to put mu back into the x, I'll just take the arc sine of both sides here. So taking the arc sine of both sides will cancel out the sine on the right side, leave me with a mu on the right side and an arc sine of x at the left side. So mu is equal to the arc sine of x. That's 1/2 times the arc sine of mu. X, I mean. Now for the second one, it requires another identity. Namely that sine 2 mu is equal to sine mu times cosine mu. Okay. Or rather, it's a 2 sine mu times cosine mu. So once I put this back, I'll be left with a 1/2 times sine mu cosine mu plus c. And we'll go back to our identities over here. So cosine mu here is the same as the square root of 1 minus x squared. And again, sine mu is equal to just x. So the final answer of my integral will be 1/2 arc sine of x plus 1/2 times x times the square root of 1 minus x squared plus c. And there you have it.